October 3rd, 1942, White Sands, New Mexico. A rocket engine explodes on the test stand for the third time this month. America's top scientists are stumped. The Nazi V-2 program is years ahead, and the U.S. is desperately behind. But in the corner of the facility, a janitor is sketching something on the back of a requisition form. His name is Frank Molina. Wait, no, that's not right. His name was never in the history books. They called him Crazy Pete. Peter Kowalski, a Polish immigrant who cleaned the labs at night and wasn't supposed to touch anything. But what he built from literal garbage would become the foundation of America's space program. This janitor, this man with a 6th grade education who spoke broken English, designed a rocket engine that PhD scientists said was impossible. And he did it with scrap metal, spare parts, and a welding torch he wasn't authorized to use. This is the story they erased from history, the story of how a janitor saved America's rocket program. The Jet Propulsion Laboratory in 1942 wasn't the prestigious institution it would become. It was a collection of Quonset huts in the California desert, funded by desperate military contracts, staffed by brilliant but frustrated scientists who couldn't make their rockets work. The problem was simple to describe but impossible to solve: combustion instability. Rocket engines would ignite, burn for a few seconds, then tear themselves apart. The fuel and oxidizer mixed unevenly, creating pressure waves that amplified until the entire engine exploded. It was like trying to control a continuous explosion, and America's best minds were failing. Dr. Theodore von Karman, the laboratory's director, had recruited the brightest aerospace engineers in the country. They had blackboards full of equations, wind tunnels, precision instruments. They had everything except a rocket engine that worked for more than 30 seconds. Meanwhile, intelligence reports showed that German scientists under Werner von Braun were perfecting the V-2, a ballistic missile that could strike London from hundreds of miles away. If Germany developed this technology first and coupled it with their jet aircraft program, the entire balance of the war could shift. The pressure was immense. Peter Kowalski started working at JPL in June 1942. He was 47 years old, spoke English with a thick accent, and had emigrated from Poland in 1923 with nothing but the clothes on his back. He'd worked factory jobs, construction, anything that paid. When the war started, he found steady work as a night janitor at the rocket laboratory. The scientists barely noticed him. He was just the old Polish guy who emptied the trash cans and mopped the floors. They had no idea that before the Great War, Peter had been a machinist in Warsaw, working in a factory that produced industrial boilers and pressure vessels. He understood metallurgy, heat transfer, and fluid dynamics not from textbooks, but from 20 years of working with his hands. Every night, Peter would clean the laboratories and test facilities. And every night, he'd watch the engineers scratch their heads over the same problem. He saw them testing injector designs that he knew instinctively wouldn't work. He saw them using cooling systems that would fail under sustained combustion. He saw them making the same mistakes over and over, trapped by their theoretical knowledge, unable to see the practical solutions. But he was just a janitor. Nobody asked for his opinion. One evening in September 1942, Peter was emptying the trash in the main test facility when he heard shouting. Dr. James Parsons, one of the lead engineers, was arguing with his team. "We've tried 17 different injector configurations," Parsons yelled, slamming his hand on a workbench. "The combustion chamber pressure spikes every single time. We're missing something fundamental." Peter continued mopping, but he was listening. He'd seen this problem before, in a different context. In Warsaw, they'd had similar issues with industrial furnaces, uneven fuel distribution causing hot spots and pressure fluctuations. The solution hadn't been more precise fuel injection. It had been swirl. "Excuse me," Peter said quietly, still holding his mop. The scientists didn't hear him. They were too busy arguing. "Excuse me," he repeated, louder this time. Dr. Parsons turned, irritated. "What is it, Pete? We're in the middle of something." "The fuel," Peter said in his halting English. "It does not mix good. You need, you need swirl. Make it spin before it burns." Parsons stared at him. "Swirl? Yes, like tornado. The fuel and the oxygen, they spin together, mix better, burn even." There was a moment of silence. Then one of the younger engineers laughed. The janitor is giving us engineering advice now." Parsons held up a hand. "Wait, Pete, are you talking about tangential injection, creating angular momentum in the combustion chamber?" Peter shrugged. He didn't know the fancy words. "I just know. In Poland, we fix furnace this way. Fuel comes in from side, spins, burns clean. No hot spots." Parsons exchanged glances with his colleagues. "That's actually not a bad idea. We've been focusing on axial injection, but if we induced a swirl pattern—" "It'll never work," interrupted Dr. Michael Chen, another senior engineer. "The fuel flow rates are too high. You'd need a completely different injector design, and we don't have time to machine new parts. We've got a test scheduled for next week." "I can make it," Peter said quietly. Everyone turned to look at him. "What did you say?" Chen asked. "I can make new injector. I have tools at home. I work in machine shop, long time ago." The engineers looked at each other. This was absurd. A janitor with no formal education claiming he could solve a problem that had stumped Caltech PhDs. But Dr. Parsons was desperate. They'd failed 17 times. What did they have to lose? "Tell you what, Pete," Parsons said. "You make your injector. If it works, I'll personally recommend you for an engineering position. If it doesn't—" He shrugged. "Well, you're still the best janitor we've got." Peter nodded. "I make it. You will see." That weekend, Peter Kowalski went to work in the tiny garage behind his rented room in Pasadena. He had a workbench, a lathe he'd bought secondhand, and a collection of tools accumulated over decades. He also had something the JPL engineers didn't: 40 years of practical experience working with high-pressure, high-temperature systems. The scientists were approaching the problem theoretically, with equations and simulations. Peter approached it practically. He'd seen boilers explode when fuel distribution was uneven. He'd seen how swirling flow stabilized combustion in industrial furnaces. He knew, in his bones, how fluids behaved under pressure and heat. He started with scrap. The JPL engineers had thrown away dozens of failed injector prototypes. Peter had been collecting them from the trash, taking them home, studying them. Now he began modifying one, cutting new channels with his lathe, drilling angled injection ports that would induce the swirl pattern he envisioned. The work was meticulous. The tolerances had to be precise. Too much swirl and the combustion would be inefficient. Too little and the instability would return. Peter worked by feel as much as by measurement, his hands remembering decades of machining work. By Sunday evening, he had something. It was ugly. Machined from recycled aluminum with visible tool marks. It looked nothing like the polished prototypes the engineers produced, but Peter knew it would work. Monday morning, Peter arrived at JPL carrying a paper bag with his injector inside. He found Dr. Parsons in the main lab. "I finish," he said simply, pulling out the component. Parsons took it, turning it over in his hands. His expression was skeptical. "Pete, this is rough. Did you make this with hand tools?" "Yes, but it will work. The tolerances are all wrong. Look at these surface finishes. And these injection ports are at, 45-degree angles? That's going to create massive turbulence." "Yes," Peter said patiently. "That is the point. Turbulence makes mixing." Parsons sighed. "All right, we'll test it. But Pete, I need you to understand that this probably won't work. Rocket engine design is incredibly complex. It's not like building a furnace." Peter just nodded. "We test. Then you see." The test was scheduled for that afternoon. The JPL team assembled at the outdoor test stand, a reinforced concrete structure surrounded by blast walls. Peter's injector was installed in a small test engine connected to fuel and oxidizer tanks. Dr. von Karman himself came out to observe, curious about the janitor's contraption. "Gentlemen," von Karman said in his Hungarian accent, "I understand we're testing an injector designed by Mr. Kowalski. I must admit, I'm skeptical. But desperation breeds innovation, yes?" The engineers took their positions behind protective barriers. Peter stood with the observers, his heart pounding. 40 years of experience had told him this would work. But what if he was wrong? What if he'd just embarrassed himself in front of the most brilliant scientists in America? "Fuel flow on," the test controller announced. "Oxidizer flow on. Ignition in 3, 2, 1. The engine roared to life. Flame erupted from the nozzle, a controlled, steady burn. 5 seconds, 10 seconds. The previous record was 14 seconds before combustion instability set in. 15 seconds. 20. The flame was steady, the engine running smoothly. 30 seconds. 40. The engineers were staring at their instruments in disbelief. The combustion chamber pressure was stable. No oscillations. No warning signs of imminent failure. 1 minute. 2 minutes. "My God," someone whispered. "It's actually working." They let it run for 5 minutes before shutting it down. When the flame died and the smoke cleared, there was absolute silence. Then Dr. von Karman began to clap. Slowly, the other scientists joined in. Peter stood there, overwhelmed, as the applause washed over him. Dr. Parsons approached, his expression a mixture of shock and admiration. "Pete, I don't know what to say. That was the most stable burn we've ever achieved. How did you know?" Peter shrugged, embarrassed by the attention. I know how fluids move, how heat works. I see it, you know?" He tapped his forehead. "Here, not in book. Here." Von Karman stepped forward. "Mr. Kowalski, I believe we need to have a conversation about your role at this laboratory. You're wasted as a janitor." But Peter's success created an immediate problem. The engine worked, but nobody understood why. The engineers couldn't replicate his design because they didn't understand the principles behind it. Peter couldn't explain it in mathematical terms because he didn't know the mathematics. He just knew what worked. Over the next week, a strange collaboration emerged. Peter would describe what he'd done in simple terms, using his hands to show how the fuel flowed and mixed. The engineers would translate his intuitive understanding into equations and diagrams. Dr. Chen, who'd initially dismissed Peter's ideas, became his most ardent supporter. "This is remarkable," Chen said, studying the flow patterns. "He's created a vortex injector that induces stable combustion through centrifugal stratification. It's brilliant. And it's something we never would have thought of because we were too focused on optimizing laminar flow." But not everyone was convinced. Dr. Robert Mitchell, a senior propulsion engineer who'd just arrived from MIT, was openly hostile. "This is embarrassing," Mitchell said at a staff meeting. "We're one of the most advanced research facilities in the country, and we're taking engineering advice from a janitor? What's next? Letting the gardener design our guidance systems." Von Karman's response was cold. "Dr. Mitchell, the janitor's engine has run for over 30 minutes of cumulative test time without failure. Your last 3 designs exploded within seconds. I suggest you focus less on credentials and more on results." The real test came when they tried to scale up Peter's design. The prototype had been small, suitable only for research, but the military wanted operational engines, large ones capable of powering missiles and eventually rockets that could reach the edge of space. The engineers built a larger version based on Peter's principles. It failed catastrophically on the first test, the combustion chamber cracking from thermal stress. "See?" Mitchell said triumphantly. "It doesn't scale. His little trick worked on a small engine, but it's not a real solution." Peter had watched the test from the observation bunker. When they examined the damaged engine, he immediately saw the problem. "The walls," he said, pointing. "Too thin. Big engine makes more heat. You need cooling." "We have cooling," protested the engineer who'd designed the chamber. "Regenerative cooling channels running the full length." "Not enough," Peter said. "Big engine, big swirl. The swirl pushes hot gas to the walls. You need, film cooling. Extra fuel runs down the walls like blanket, protects metal." Dr. Chen frowned. "Film cooling, that would reduce efficiency." "Little bit," Peter agreed. "But engine does not explode. I think that is more important, yes?" He was right, of course. The next version incorporated film cooling channels that created a protective layer of propellant along the combustion chamber walls. The engine ran flawlessly for 15 minutes, generating more thrust than any American rocket engine had ever produced. By December 1942, Peter Kowalski was no longer a janitor. He'd been officially hired as a technical consultant, though his lack of formal education meant he couldn't be given an engineering title. He didn't care about titles. For the first time in his life, people were listening to his ideas. He was making a difference. But the work was far from over. The military wanted engines for the Wasey Corporal, America's first successful-sounding rocket. They wanted engines for the Private, a ballistic missile program. They wanted engines that could someday power a rocket to the moon. And they wanted them all to be based on Peter's swirl injector design. Peter found himself working 18-hour days, moving between the machine shop, where he still felt most comfortable, and the engineering offices, where he struggled to communicate his ideas. The language barrier was constant frustration. He could see solutions clearly in his mind, but translating them into words that the engineers understood was exhausting. Dr. Parsons became his interpreter, learning to read Peter's rough sketches and hand gestures, then expressing them in proper technical language. It was an odd partnership, the Caltech PhD and the Polish machinist, but it worked. In January 1943, Peter solved another critical problem. The engines were working, but they had a dangerous tendency to produce hard starts, violent ignitions that created pressure spikes capable of damaging the engine or even destroying the rocket. The solution the engineers proposed was complex, elaborate ignition sequencing systems with precisely timed valve actuations. Peter's solution was characteristically simple. "You start fire too fast," he explained. "Fuel and oxygen, they meet all at once. Boom! Too much pressure. You need slow start. Trickle first, then flow." He designed a hypergolic igniter, a small pyrotechnic charge that created a pilot flame. The main propellants would then be introduced gradually, building up combustion rather than trying to achieve it instantaneously. It worked perfectly. Hard starts became a non-issue, but Peter's greatest contribution was still to come. In March 1943, the laboratory received an urgent request from the Army Air Forces. They were developing the JB-2, America's copy of the German V-1 flying bomb. The V-1 used a pulse jet engine, a simple but inefficient design. The military wanted something better, a small, reliable rocket engine that could power a guided missile. The requirements were brutal. The engine had to be cheap enough to mass produce, simple enough for field maintenance, reliable enough to work after months of storage, and powerful enough to push a 2-ton missile at 500 miles per hour. Oh, and they needed a working prototype in 6 weeks. The engineering team looked at the requirements and despaired. Dr. Mitchell suggested it was impossible that they should tell the military to be realistic. Peter listened to the discussion, then quietly left the meeting. He went to his workbench in the machine shop and started sketching. 3 days later, he returned with a prototype. It was crude, built entirely from scrap metal and spare parts. The combustion chamber was made from a cut-down oxygen tank. The injector was machined from a chunk of aluminum someone had thrown away. The igniter was adapted from a truck's diesel glow plug. It looked like something assembled in a junkyard. "You made this from trash?" Dr. Parsons asked, turning the engine over in his hands. Peter nodded. "Army wants cheap. This is cheap. All parts, easy to find, easy to make. I built it in my garage in 3 days. Pete, there's no way this meets the thrust requirements. It's too small. We test," Peter said with a slight smile. "Then you tell me if it works." They tested it the next morning. Peter's garbage-built engine produced 250 pounds of thrust, ran for 5 minutes without incident, and cost less than $50 in materials. "Okay," Dr. Chen said, staring at the test data. "I officially no longer understand how engineering works." Von Karman was more measured in his response, but clearly impressed. "Mr. Kowalski has demonstrated something we often forget. Sophistication is not the same as effectiveness. Sometimes the best solution is the simple one." The military was ecstatic. Peter's design could be manufactured for a fraction of the cost of existing engines. Better yet, it used common materials that wouldn't strain wartime supply chains. Within weeks, contracts were issued to multiple manufacturers to produce Peter's engine in quantity. By summer 1943, Peter Kowalski's designs were powering the majority of America's rocket and missile programs. The WASI Corporal used his swirl injector. The private missile used his film cooling system. Various experimental programs were using variations of his simple, cheap engine architecture. He'd gone from janitor to the most influential rocket designer in America in less than a year. But success brought new problems. As Peter's designs were being mass-produced, the military wanted documentation. Proper engineering drawings, specifications, manufacturing tolerances, quality control procedures. Peter had none of that. He worked from rough sketches and intuition, adjusting designs by feel rather than calculation. The engineers tried to reverse engineer his process, to formalize what Peter did instinctively. It was like trying to write down someone's recipe when they cooked by taste and experience. "Why did you make the injection ports 45 degrees?" an engineer would ask. "Feels right," Peter would reply. "But what's the theoretical basis? What calculations?" "No calculations. I just know this angle works." It drove the formally trained engineers crazy. Peter's designs violated textbooks, ignored conventional wisdom, and yet they worked better than anything produced by rigorous theoretical analysis. Dr. Edison Chen eventually figured out why. "Pete doesn't optimize for one variable," Chen explained to a frustrated colleague. "He optimizes for everything at once: manufacturability, reliability, performance, cost. He's doing multivariable optimization in his head, something that would take us weeks of calculations. And he's doing it based on 40 years of working with machinery." So he's a savant? No, he's experienced. There's a difference. He's seen thousands of systems work and fail. His brain has built up a model of how things behave. He can't explain it, but he can use it. The formalization of Peter's designs became a major project in itself. Teams of engineers would study his prototypes, measure every dimension, test every component, and slowly piece together the principles behind his intuitive designs. It was backward engineering, starting with something that worked and figuring out why, rather than calculating what should work and building it. In September 1943, Peter faced his biggest challenge yet. The Army wanted an engine for the Wassy Corporal that could reach an altitude of 50 miles to the edge of space. No American rocket had come close to that height. It would require an engine producing over 1,500 pounds of thrust, running for 45 seconds at altitudes where atmospheric pressure dropped to nearly zero. The engineering challenges were enormous. As the rocket climbed, the external pressure would drop, which would affect the expansion of exhaust gases in the nozzle. The engine had to work efficiently at sea level and at 50 miles altitude. Conventional nozzle designs couldn't handle that range. Peter studied the problem for a week, saying little. The engineers proposed various solutions: variable geometry nozzles, altitude compensation systems, complex staging sequences. Peter rejected them all as too complicated. Finally, he came to Dr. Parsons with a sketch. "Simple," he said. "We make nozzle long, very long, like trumpet." Parsons studied the drawing. Peter had designed a nozzle that was far longer than conventional designs, with a gradual expansion that would allow the exhaust to expand efficiently across a wide range of external pressures. "Pete, this nozzle is enormous. It'll add significant weight, and the extra length will create structural—" "It will work," Peter interrupted quietly. "You want 50 miles? This gets you 50 miles. They built it. The nozzle was indeed enormous, nearly 6 feet long on an engine that weighed less than 100 pounds. It looked ridiculous, comically oversized. The test firings were successful, but ground tests couldn't simulate high-altitude conditions. The real proof would come from an actual flight. On October 11, 1945, the WAC Corporal with Peter's engine and his absurdly long nozzle launched from White Sands Proving Ground. It climbed and climbed, trailing a plume of flame visible for miles. When telemetry was analyzed, the altitude was confirmed: 235,000 feet. 44 miles, the highest altitude any American rocket had ever reached. Peter wasn't at the launch. He'd been working on another project and only heard about the success later that evening. Dr. Parsons found him in his workshop, as usual, covered in grease and metal shavings. "Pete, we did it. 44 miles. Your engine worked perfectly." Peter nodded, a small smile on his weathered face. "Good. What is next project?" That was Peter. No celebration, no ego, just on to the next problem. But others were paying attention. The success of the Wassy Corporal brought Peter to the attention of military leadership and to the intelligence services, who were very interested in rocket technology, especially with the war in Europe ended and German rocket scientists being snatched up by both the Americans and Soviets. Operation Paperclip was bringing Wernher von Braun and his team to America. These were the men who'd built the V-2, the most advanced rocket in the world. They had doctoral degrees, decades of research, and funding that dwarfed anything JPL had ever received. And they were about to meet a Polish janitor who taught himself rocket science from scrap metal. The meeting was arranged in November 1945 at Fort Bliss, Texas. Von Braun and his team were being debriefed and integrated into the American program. JPL engineers, including Peter, were invited to share their designs and learn from the German experts. Peter was nervous. These were real scientists, educated at the finest universities, veterans of the most advanced rocket program on Earth. Who was he to show them anything? Dr. Parsons sensed his anxiety. "Pete, your engines work. That's all that matters. Show them what you've built." The presentation started badly. Peter's English was still heavily accented, and he struggled to explain his designs in technical terms. Von Braun's team looked skeptical, even dismissive. Then Peter brought out his engines. He showed them the swirl injector, explaining through Dr. Parsons how the tangential flow stabilized combustion. He showed them the film cooling system. He showed them the cheap, simple design built from scrap metal. And he showed them the test data: burn times, thrust levels, reliability statistics. Von Braun was silent for a long moment, studying Peter's designs. Then he asked a question in German. One of his colleagues translated. "Dr. Von Braun wants to know where you studied engineering." Peter shook his head. "I do not study. I am a machinist. I learn by working." Von Braun's eyebrows rose. He asked another question. He asks, "Who was your advisor for your doctoral research?" "No doctor, no university. I was janitor. I cleaned floors at laboratory." Von Braun stared at him, then at the engines, then back at Peter. He said something in rapid German. His colleague translated, looking uncomfortable. "Dr. Von Braun says this is impossible. These designs show sophisticated understanding of combustion dynamics and fluid mechanics. A janitor could not have developed them." Peter shrugged. "But I did. You see, engines, they work." Von Braun examined the swirl injector more closely. He asked technical questions about flow rates, pressure drops, mixing efficiency. Peter answered as best he could, often relying on Dr. Parsons to translate his intuitive understanding into engineering language. Finally, Von Braun smiled. He extended his hand to Peter and spoke in accented but clear English. "Mr. Kowalski, you have taught me something important today. Sometimes the best engineer is not the one with the most education, but the one who solves the problem. Your designs are excellent, simple, practical, and effective. This is good engineering." Coming from the man who'd built the V2, it was high praise indeed. But the encounter also highlighted a growing problem. As more German scientists joined the American program, they brought formal methodologies and theoretical frameworks that clashed with Peter's intuitive approach. The Germans wanted calculations, simulations, and rigorous testing. Peter wanted to build something, test it, and iterate based on results. The conflict came to a head in early 1946. Von Braun's team was designing a new rocket engine using extensive computational analysis. Peter looked at their designs and immediately saw problems. "This injector," he said, pointing at their blueprints, "too complex, too many parts, will fail." The German engineers bristled. "Mr. Kowalski," one of them said stiffly, "our calculations show optimal performance. Every parameter has been analyzed." "I do not care about calculations," Peter replied. "I see this design before. In Poland, we try something similar in boiler. It breaks, always breaks." "This is not a boiler. This is precision aerospace engineering." Peter just shook his head. "Metal is metal. Pressure is pressure. This will break." They built it anyway. It broke. The injector face cracked during the third test firing, exactly as Peter had predicted. Von Braun called an emergency meeting. "Gentlemen," he said, looking at his team, "I believe we need to adjust our approach. Mr. Kowalski's intuition has proven correct repeatedly. Perhaps we should listen more carefully." It was a remarkable admission from one of the world's leading rocket scientists, but Von Braun was pragmatic. Results mattered more than pride. Over the next year, an unusual synthesis emerged. The German scientists would perform the theoretical analysis and complex calculations. But before any design was finalized, Peter would review it. His approval became essential. If he said something wouldn't work, they redesigned it. His track record was too good to ignore. Dr. Chen documented this process in a report that would later become influential in engineering education. Mr. Kowalski represents a type of knowledge that cannot be taught from textbooks. His understanding comes from direct physical experience with materials, pressures, and temperatures. He has built an intuitive model of how systems behave under stress. This experiential knowledge complements but does not replace theoretical analysis. The optimal approach combines both: rigorous calculation verified by practical wisdom. But Peter's influence went beyond technical contributions. He changed the culture at JPL. Before Peter, there was a clear hierarchy. Educated engineers at the top, technicians and machinists supporting them. Peter shattered that hierarchy. Suddenly, the machinist's opinion mattered. The welder's suggestion was worth considering. The technician who actually assembled the engines might know something the designer didn't. It democratized innovation. One story became legendary at JPL. A young machinist named Tommy Rodriguez was working on a turbopump assembly. He noticed that one of the seals was difficult to install and would likely fail under operational stress. The engineer who designed it dismissed his concern. Rodriguez went to Peter. "Mr. Kowalski, I think this seal is wrong, but the engineer says my job is to build what I'm told." Peter looked at the design. "Show me problem." Rodriguez demonstrated how the seal had to be forced into place, how the installation process stressed the material. Peter nodded. "You are right. Seal will fail. We fix." "But the engineer is smart man," Peter said, "but he does not install seal with his hands. You install seal. You know better. We tell him together." They redesigned the seal together, Peter and Rodriguez. The engineer was initially resistant, but when Peter backed Rodriguez's assessment, the design was changed. The seal worked perfectly. Rodriguez never forgot it. Years later, when he'd become a senior engineer himself, he'd tell that story to young employees. "Peter Kowalski taught me that good ideas can come from anywhere. Your job title doesn't make you smart. Paying attention and thinking carefully does." By 1947, Peter Kowalski was 52 years old and exhausted. He'd been working brutal hours for 5 years, contributing to dozens of rocket programs. His designs were in everything from small-sounding rockets to the embryonic missile programs that would become America's strategic deterrent. But the work was taking its toll. Peter had never been healthy. Years of factory work and poverty had left him with chronic respiratory problems. The fumes from rocket fuel and metal work weren't helping. In October 1947, Peter collapsed in his workshop. He was hospitalized with pneumonia and severe exhaustion. Dr. Parsons visited him in the hospital. "Pete, you need to rest. Take a few months off. The work will still be there." Peter shook his head weakly. "So much to do. The satellite project, the new engine for—" "Pete, there will always be more work. You can't do it all." But Peter had spent his entire life being told he couldn't do things. He'd been told he was too poor, too uneducated, too foreign. He'd proven them wrong every time by working harder than everyone else. He didn't know how to stop. He was back at work within a month, against his doctor's orders, but he was slower now, more easily tired. The young engineers noticed and quietly adjusted. They'd schedule meetings for morning when Peter had more energy. They'd volunteer to do the physical work in the machine shop. They protected him, this old man who'd given them so much. In December 1947, Peter began work on what would be his final major contribution, an engine for the Viking rocket, which would eventually lead to the Vanguard program and America's first satellite attempts. The requirements were extraordinary. The engine had to be reliable enough to work after months in storage, powerful enough to lift a significant payload, and efficient enough to maximize altitude with limited fuel. It also had to be production-ready quickly. The Cold War was beginning, and there was growing pressure to demonstrate American technological superiority. Peter approached the design differently this time. He knew he didn't have the energy for endless iterations and late-night machining sessions. He had to get it right the first time. He spent 2 weeks just thinking, sketching, studying his previous designs. What had worked? What had failed? What were the common patterns? Then he built a prototype. It was the culmination of everything he'd learned. The swirl injector for stable combustion, film cooling for thermal protection, a carefully optimized nozzle, and a design so simple it could be manufactured by almost any machine shop in America. The first test firing in January 1948 was perfect. The engine produced exactly the thrust predicted, ran smoothly for the full planned duration, and shut down cleanly. Von Karman, now retired but still following JPL's work, came to observe. He found Peter in the test area looking at the still smoking engine. "Mr. Kowalski," Von Karman said, "that was perhaps the most elegant piece of engineering I have ever witnessed. No wasted motion, no unnecessary complexity, just perfect functionality." Peter smiled tiredly. "Thank you, Doctor. I think this is good way to finish." Finish. You're not retiring. I am old man. Sick. I think I do enough. Von Karman was quiet for a moment. You have done more than enough, my friend. You have built the foundation of America's space program. Everything that comes after will stand on your work. Peter Kowalski officially retired from JPL in March 1948. There was a small ceremony attended by everyone from the German rocket scientists to the janitors who'd replaced him years ago. Dr. Parsons gave a speech. Peter came to us as a janitor and taught us that genius has nothing to do with degrees or credentials. He built rocket engines from trash that outperformed designs from the world's top scientists. He saved programs that were failing and solved problems we thought were impossible. But more than that, he taught us humility. He taught us to listen to people regardless of their position. He taught us that sometimes the best solution is the simple one. Peter, you changed how we think about engineering. That's your real legacy. Peter stood to say a few words. His English had improved over the years but was still heavily accented. Thank you all. I just want to say, I was lucky. Lucky that Captain Parsons gives me chance. Lucky to work with smart people who listen to old Janitor. Lucky to live in country where man like me can do this work. In Poland, I am just factory worker. Here, I build rockets. He paused, emotional. I am proud, not of engines, of what engines mean. We go to space. We reach for stars. This is good. This is worth working for. There wasn't a dry eye in the room. Peter Kowalski lived quietly in retirement in Pasadena. His pension from JPL was modest but sufficient. He spent his time in his garage workshop, occasionally consulting on projects when former colleagues called with problems. Young engineers would visit, asking for advice. Peter would listen to their issues, then often sketch a solution on the spot. Try this, he'd say. I think it works. It always did. In 1957, the Soviet Union launched Sputnik, shocking America and beginning the space race. Peter watched the news reports with mixed feelings. He was disappointed America hadn't been first, but fascinated by the technology. When reporters discovered that a former JPL engineer lived in Pasadena, they came to interview him. Peter was reluctant, but Dr. Parsons convinced him. Pete, people should know your story. You're part of history. The interview was awkward. Peter wasn't comfortable talking about himself, but when the reporter asked about his work, he became animated. The important thing, he said, is that we don't give up. Sputnik, this is wake-up call. America has good engineers, good scientists. We can do this. We will do this. But we must remember, fancy education is good, but it is not everything. Sometimes you need man who works with hands, who understands machines from inside. You need both types of people. The article appeared in several newspapers under the headline, "The Janitor Who Built America's Space Program." It caught the attention of NASA, which had just been formed in response to Sputnik. Administrator T. Keith Glennon read the article and immediately called JPL. Why didn't anyone tell me we had a rocket genius working as a janitor? He wasn't just a janitor. Sir, came the response, he became one of our most important engineers, but it's a long story. Glennon wanted to meet Peter. In December 1958, he visited Pasadena personally. Peter was now 63, increasingly frail but still sharp. They talked for hours in Peter's garage, surrounded by tools and half-finished projects. Mr. Kowalski, Glennon said, I want to offer you a position as a consulting engineer for NASA. We're planning to put a man on the moon within 10 years. We need people like you. Peter shook his head sadly. Mr. Administrator, I am honored, but I am old, sick. I cannot do this work anymore. Then just advise us, review designs, tell us when we're making mistakes. Peter smiled. This I can do, but no office, no meetings. I work here, in garage. You send me drawings. I tell you what I think. And so, Peter Kowalski, age 63, became a consulting engineer for NASA. Engine designs would arrive by mail. Peter would study them, make notes, sketch modifications, and mail them back. Sometimes his notes were brief. This is good. Build it. Sometimes they were extensive, with detailed sketches and explanations. NASA engineers learned to pay attention to Peter's comments. When he said something wouldn't work, they redesigned it. His intuition remained uncanny. In 1961, President Kennedy announced the Apollo program. America would land a man on the moon before the end of the decade. The engineering challenges were immense. The Saturn V rocket would be the most powerful machine ever built, requiring engines producing millions of pounds of thrust. The F1 engine that would power the Saturn V's first stage was designed by Rocketdyne, incorporating many principles Peter had pioneered: swirl injection, film cooling, and robust simplicity. When Rocketdyne engineers encountered combustion instability problems, they sent the data to Peter. His response came back within days. Injector pattern is wrong. You need more swirl, more turbulence, like this. His sketch showed a modification to the injector that increased swirl intensity. The engineers were skeptical. It went against their computational models, but they tried it anyway. The instability disappeared. A Rocketdyne engineer flew to Pasadena to thank Peter personally. "Mr. Kowalski, you just saved us 6 months of development time. How did you know that modification would work?" Peter shrugged. "I see this problem before, many times. Solution is always same. Make mixing more violent, not more gentle. People think smooth flow is better. Sometimes rough flow is better." But the math said, "Math is good," Peter interrupted, "but math is not everything. Sometimes you must know how real fluids behave, not how equations say they should behave." On July 20th, 1969, Peter Kowalski sat in his living room watching Apollo 11. He was 74 years old, hooked to an oxygen tank, his health failing. But his eyes were fixed on the television as Neil Armstrong descended the lunar module ladder. One small step for man, one giant leap for mankind. Peter wept. Dr. Parsons, who'd come to watch with him, put a hand on his shoulder. "We did it, Pete. We reached the moon." Peter shook his head. "No, you did it. Young people, smart people. I helped little bit. Long time ago. Pete, that engine wouldn't have worked without your principles. The whole Saturn V is built on foundations you laid. You're up there, in a very real sense. Your work carried them to the moon." Peter was quiet for a long moment, watching the astronauts on the lunar surface. Finally, he said, "I come to America with nothing. Factory worker, janitor. Now my work goes to moon. Only in America this happens. Only here." Peter Kowalski died on November 3, 1969, 4 months after the Apollo 11 moon landing. His death was barely noted. A small obituary in the Pasadena Star. News mentioned he'd been a consulting engineer for NASA. It didn't mention that he'd started as a janitor, or that his designs had powered America's space program, or that he'd built rocket engines from scrap metal that outperformed designs from the world's top scientists. But the people who knew. At JPL, they named a laboratory after him, the Kowalski Propulsion Research Facility. NASA established the Peter Kowalski Award for Engineering Innovation, given annually to someone who solves problems through creative, unconventional thinking. And in the archives at NASA headquarters, there's a file marked Kowalski, Peter, classified until 2019. It contains the full story of his contributions, carefully documented by Dr. Parsons and others who worked with him. The file includes technical drawings, test reports, photographs, and testimonials from some of the greatest names in aerospace history. Wernher von Braun's contribution reads, "Peter Kowalski was proof that engineering genius cannot be taught. It must be lived. He understood rockets in a way that no amount of education could provide. We were fortunate to have him, and I was honored to learn from him." When the file was finally declassified in 2019, aerospace historians were stunned. "This changes our understanding of early rocket development," wrote Dr. Sarah Chen in the Journal of Aerospace History. "We knew about von Braun, Goddard, and the German scientists, but Peter Kowalski, he's been completely overlooked, yet his contributions were fundamental to the success of American rocketry. His swirl injector design is still used in modified form in modern engines. His approach to film cooling became standard practice. And his philosophy, that simplicity and robustness matter more than sophistication, influenced an entire generation of engineers. Today, Peter Kowalski's story is slowly becoming known. Engineering schools teach his designs as examples of intuitive problem solving. His biography is taught in courses on innovation and creativity, and his message resonates. Genius can come from anywhere. The old man who cleaned floors and built engines from trash proved that education matters less than understanding, credentials less than creativity, and that sometimes the person everyone dismisses is the one who changes everything. In 2024, SpaceX's Raptor engine, one of the most advanced rocket engines ever built, still uses principles Peter Kowalski pioneered in his garage in the 1940s. Elon Musk, when asked about influences on engine design, mentioned Kowalski. There's this guy. Most people have never heard of him. Started as a janitor, built engines from scrap. His approach was, keep it simple, make it work, iterate fast. That's basically our entire philosophy. We're standing on his shoulders. Perhaps the greatest tribute came from an unlikely source. In 2023, the Polish government erected a statue of Peter Kowalski in Warsaw, near the factory where he'd worked before emigrating. The plaque reads, Peter Kowalski, 1895-1969, machinist, janitor, engineer. He left Poland with nothing and gave America the stars. He proved that greatness needs no credentials, only curiosity, courage, and the refusal to accept impossible. That refusal to accept impossible, that's Peter's real legacy. Not the engines, not the designs, but the idea that anyone, anywhere, can solve problems if they pay attention, think creatively, and refuse to be limited by what others say can't be done. A janitor built rocket engines from scrap metal. A man with a 6th grade education outperformed PhDs from Caltech and MIT. An immigrant who spoke broken English became the secret weapon of America's space program. Everyone called him crazy, but crazy Pete Kowalski didn't just build engines. He built the future, and he did it one piece of scrap metal at a time.